Tech. I've been with Fisher & Tech for the past 5 years. Prior to that, I spent 8 years in industry as a design and analysis engineer. So dealing with injection molding, design for manufacture, flow simulation, finite element analysis, as well as general design. So ultimately, what the agenda of today is going to be is really going to get you guys familiar with what SOLIDWORKS Plastics is, really step you through the interface of SOLIDWORKS Plastics with a plastics project. Then we'll get into kind of true kind of manufactured, looking at multi-cavity molds, and then how to actually utilize SOLIDWORKS Plastics to aid in runner design. I thought it'd be really kind of cool to take a look at a pretty common example. Specifically, a lot of injection molding goes into parts for automotive, and I just wanted to grab a windshield wiper holder, just a real common injection molded part, and that's the part we're going to be taking a look at today. So that's really what we're going to be looking at, and we'll have some time at the end for some questions and answers. Anything you see today, feel free to ask questions. I'll be happy to answer them at the end of today's webinar. Before I jump in, just kind of what you're aware of, and I'll go over this when we jump into plastics. The analysis portfolio, you kind of see right today we're dealing with plastics, and we'll be dealing with plastic, standard, professional, and premium. I'll show you a little bit of each and kind of detail what the distinctions are between each of the packages. But if you have any other type of analysis needs, this kind of shows you what we sort of offer within the SOLIDWORKS simulation portfolio, as well as you see to the right some of the partner products we offer for analysis needs. So ultimately, if you have any types of questions about any of them, whether it pertains to plastics, or if you have a question about FEA or CFD, or even Inspire, EMWorks, feel free to reach out to us. I'd be happy to answer those questions, or your account manager would be happy to answer those questions. All right, so what we're going to really jump into first is we're going to utilize SOLIDWORKS Plastics to simulate plastic flow of one single windshield wiper holder. I'm going to step you through how to set up a project within SOLIDWORKS Plastics and kind of show you all the different things you can implement within the plastics software. And the thing you're going to see right here is some of you who are actually mold makers, tool makers, you already understand how much time it takes to build out these molds, and really you can really set up these scenarios in a variety of parts and really simulate where you're going to have problems in the actual manufacturing process, and how you can eliminate them by either changing your gate, maybe changing the overall geometry, etc. And I'll lay that out as we work our way through our first sort of part. So with that, let me jump into SOLIDWORKS. All right, so what we have here is we have a single cavity of this windshield wiper holder. The first thing I always like to point out, compared to some of the other injection molded softwares out there, I've used MoldFlow before. It's a great tool, and as well as MoldX, but MoldFlow is a third-party software, meaning that it's not integrated into a CAD platform. So when you're working within MoldFlow, you actually have to export out of CAD into your plastics injection software. That's how all the other injection molding softwares out there operate. SOLIDWORKS Plastics is a little bit different in the fact that I'm still working within the CAD interface right here. And why that's significant, when you're doing plastic part design, specifically, one of the things you may run into is short shotting. You may have a very thin wall thickness, and one of the most easy things you can do is maybe add a rib, or maybe just change the thickness. And by operating right within the SOLIDWORKS CAD interface, you can really go ahead and make those changes as you see fit. So you see I click on my model tab right here, and then if I wanted to, I could change the interface accordingly. So that's kind of a really kind of cool feature. Having experience working with some of the other injection molding softwares out there, that is a huge time saver when you have to go. You can make the change within your CAD geometry within SOLIDWORKS and not have to import and export to a third-party injection molding software. So the process of doing this is fairly user intuitive. I'm going to step you through exactly everything we need to know. in terms of how to set up a plastics project. The first step in any plastics project is you set up your mesh. So if we set up our mesh right here, a couple things I'll point out right here. So those of you who are very familiar with utilizing tool makers, the most common question I get asked is, specifically, you know, do I have the ability to add custom gates? So you see right here, I have an edge gate, I have a submarine gate, and a banana gate that's pre-built into the software, as well as a multi-cavity one-side layout, a star layout, and a two-sided layout. Additionally, because this is all CAD-based, I mean, if you actually physically model the sprues and maybe you have a custom gate, you can draw those out and then utilize them via the injection location method. So the mesh itself is fairly simple. You go through the process, you just sort of key in the mesh. Those of you who've worked with an FEA or CFD, it's very much the same, where you key in ultimately what your mesh size is in your part, and ultimately kind of the same rules of thumb apply for injection molding softwares. The more elements you have, the longer it takes to run computationally. Obviously, there's a balance of making sure you have enough elements that it's properly going to model the flow front. So not having it too coarse where it runs really quickly, but it's not accurately modeling the flow front. So in this case, we've meshed it to an appropriate size that's going to be accurate, but still not going to take forever to run. And then our next step in terms of setting this model up is really being able to apply our polymers. So the other thing you might notice about this is I'm just modeling the cavity. The one question I get asked is, what if I don't have the, what if I have the mold? Can I model the mold itself? Yes, you can model the mold itself. By only having the part, what you're saying is that, the mold temperature is fixed, meaning if I go to my process parameters, you see right here, I'm setting my mold temperature as constant. Now, if you have a mold with cooling lines where that temperature distribution not necessarily be constant on the cavity, you can actually physically model the mold. You see the option right here to model the mold. And then if you have cooling lines, what you would need would be SOLIDWORKS Plastics Premium, which includes the ability to apply cooling lines for your mold. In this case, the other flip side of the coin is if you have a constant mold temperature, it saves you time by not having to actually physically model the mold. So in this case, we just have the cavity, and then what we need to do is just apply the polymer that's going to be filling up that cavity. So the great thing about this database is very, 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 very large. At current, I think it's right below 5,000 materials are in the polymer database. Now, bear in mind, if you start dealing with inserts or overmolding applications or molds, there's also solid materials, which is pretty expansive. But just in the polymer material database alone, there's about a little less than 5,000. So if I look at all these, you see how each of them has kind of the standard ABS, but then it has all the different chemical makes for the polymer. So the great thing about this is you can also sort this by the company. If I sort by the company, I can go to a company and maybe I want to look at, I don't know, Dow Chemical and see everything from Dow Chemical that's within the database. So you see there's some ABSs, TPUs, and everything else that you'd necessarily want. So in this case, we're modeling this material as a I think a PET material. Yep. And the other kind of thing I want to point out is if you ever have any custom alloy, and some of you mold makers or tool makers, you're probably going to be dealing with some custom polymers at some point in time. You have the ability, you can still key in custom polymers or even custom inserts or custom mold solid materials if you want to do that. So you see in this case, if I hit edit material, everything that would be pertinent for polymers I could key in. Very much the viscosity of a polymer, your PVT data, but then some of you might be dealing with glass fibers. You can key those values in, and everything that you would want to key in, you have the ability to key in as well. The other thing I'll point out, those of you who've worked with Moldex or Moldflow, one of the things you probably recognize from those softwares is you can import bin files. If you've been working directly with a plastics manufacturer, they might send you a bin file. You can actually bring in that bin file. Or some of the new things you're seeing are actual Excel sheets where you can actually import those values into the database. So ultimately, if it doesn't fall within the 4,000 materials in the database, you still have the ability to key in that custom polymer. Okay, great. So we keyed in our polymer in this, and then the next stage of the process is really just keying up the settings for our injection molding scenario. So those of you might be referring to first stage injection, second stage injection. SolidWorks refers to it, as fill, pack, and warp. So just to kind of call out those of you who are wondering about the licenses themselves, the SolidWorks Plastics has 3 licenses, so Standard, Pro, and Premium. Standard just includes the first stage injection, which is just the fill stage. Professional, which is kind of the medium plastics package, it includes fill and pack. And then Premium, it includes fill, pack, and warpage. So you'll be able to actually see the warpage on a part. You see right here for this first stage injection process, obviously, depending on the material, you might not know what that filling time is. You can use the default for that material. Or if you have a custom application, you can actually key in the actual fill time, which, it can be quicker or slower, whatever you're sort of keying in. You also have the melt temperature of that polymer. You can always change it if it's not going to be at what the default is for that PET material we're using. And then as well as, like I sort of mentioned, we're not physically modeling the mold right here. We're just saying that the mold has a constant temperature on the cavity, and we're specifying that mold temperature as 212 degrees Fahrenheit. Obviously, again, you can change that if the mold temperature is a little bit different. The last 2 options you see right here are your machine limits. So, obviously, if you exceed your machine limits, it's not going to be able to fill. So you see your clamp force and your injection pressure limit on your machine. Obviously, your pressure is going to be much less than this, and your clamp force should be much less than this, but this is just what your machine's rated at. Additionally, there's a couple other more advanced options here I'll just point out. So you can actually specify your criteria for short shots, whatever that temperature criteria is going to be. So when you're short shotting, not able to fill up the entire cavity, you have the ability to actually apply venting. So when you run a scenario, look at your air traps and then actually apply where your venting is going to be at during a venting analysis, as well as co-injection. So if we open up the pack settings now, you see you can specify how long it's going to cool, how long pressure is going to be held in that second stage injection, and you can actually key in a custom pressure profile setting if you want, if you want to sort of change how your pressure is going to be held. And then your warp settings are just what your ambient temperature is set at and how gravity is acting on the part in the mold. Kind of last thing we can specify in this scenario is our injection location. So the thing right here, this is, we don't have a sprue modeled. You'll see in the next case with the multi-cavity mold is we actually have a runner system and a sprue set up. In this case, we're just saying it's directly going into the cavity. We can key in our pointer diameter, and we can key it by node, or if we didn't want to go by a node, maybe wanted to click on the entire face, we could do that. Additionally, if you have simultaneous gates or multiple gates, a lot of times you may have a gate and then another gate. You can actually run multiple gates within SolidWorks Plastics. That would be within Plastics Pro. And the ability to apply multiple gates, you could actually specify that gate to turn on at a set time, or maybe you say both gates are filling up, simultaneously. So really, any possible scenario in terms of how you set your gates, you have the ability to apply. So in this case, it's really kind of a basic flow problem, kind of just getting our feet wet in terms of setting this model up. You'll see in the next scenarios, we jump into a multi-cavity mold where we look at seeing how it responds, how we design our runner system, and then also look at balanced runners. But let's now take a look at our results. So if I go to my flow results, and the really cool thing about this is I have run the scenario, and now I can actually look at my results and it's going to show me, is it able to fill up? The great thing about this, if it didn't fill up, you'd see gray, and it would tell you you have a short shot. So obviously it's able to fill up for this scenario. I could always turn on what's known as the advisor, which will also tell you, hey, this part can be successfully filled with an injection pressure of 6.3 megapascals. So it's nowhere near your injection pressure limit on the machine. It's just telling you where, what your pressure is and what your fill time is. So one of the really important things when you're looking, depending on what industry you're working in, you're probably concerned about weld lines or knit lines. If you're unfamiliar with what weld lines or knit lines are, that's really just the when two of the flow fronts kind of cross over at different temperatures. What they can cause is a small little line or a sort of a non-congruity. It's not necessarily homogeneous. So if you've ever looked at a plastic part, if you ever looked on the inside of a part or on the back side of the part, the side that your consumers aren't going to be seeing, you'll find, if you know what you're looking for, you'll be able to find a weld line. And it's really important from a mold making perspective or a tool making perspective, is because you want to have those weld lines, if it's a consumer facing plastic part, not be on the consumer facing side of things. So in this case, it's on the bottom, which is connecting. It's not really an issue to me. Even on here, it's not really that often that you're looking at weld lines for a windshield wiper. But say it was a cell phone case or maybe a computer tower, something that seeing users are looking at consistently. It's nice to be able to identify where those weld lines are at. So obviously, where those weld lines are at are subject to where your gate is at, and really you could run another scenario to sort of adjust where your gate is at to sort of change how your flow front is going to occur in your model. The other really useful thing when you're setting up plastic scenarios is really to identify where your air traps are in the model. So anywhere where air is trapped in the model, purpose of this is really to apply where your vents are going to be for the tool. So as we work our way through this, we can actually go through and look at a variety of parameters. So we can look at pressure. Again, we can go to ease of fill, so you kind of see that it's pretty easy to fill. There's no struggle in the fill. Now, if you were starting to reach a clamping limit, you start to see red, or a pressure limit, you start to see red at telling you that it's difficult to fill up. So if we go to warp now, obviously you want to look at warpage. That's really how, after cooling, how much that part is deviating from its original sort of design shape. Great thing about this is we can look at warp in all X, Y, and Z directions. So there's not a lot of warp right here, but one of the cool things about this, it's a little bit hard to see. So the maximum warp is 0.033 inches. So if we and this is in the X direction. So if we look at our global triad, you see right there, that's the X direction. You can see the max warp is occurring. I can adjust my deformation scale to be larger. And it just visually shows you how the part is warping. I can do the same thing for the Y direction. Again, I have that deformation scale set higher at 15. If I go back to kind of the true scale, kind of see that it's not a significant amount of warp, as well as looking at my Z direction. And this has the most amount of warp. You're at 0.044. The others were at 0.03. But again, it's not huge in terms of what the warp value actually is. You also have the ability to look at sync marks. And everything that I'm showing right now can be saved as an image, can be saved, as JPEG, GIFs, what have you, to be sent to a customer. Additionally, there's a very nice reporting, if I go to my plastics menu right here, that I can record these animations, as well as sort of assign, kind of use like a default template report. You kind of see the report right here, where I can generate either a PowerPoint report or a Microsoft Word report, where it's going to summarize all the boundary conditions as well as all the results. And the great thing about these there's default templates built into Word, but you can customize them accordingly. Okay, great. So let's jump back here. So what we're going to jump into now is we're going to utilize a multi-cavity mold. So the kind of the true manufacture of this is the part. Now it's not going to be having a single cavity. We want to see the effect of setting this model up for kind of a standard two-sided layout, so 6 of these cavities. And one of the things when you're designing tools is you have to establish the runner system. So you see the runners right here. There's kind of these pipe designs, and you sort of see where the injection location at the top. That's the sprue kind of coming down. It's sometimes difficult to understand how large these runners need to be. And the optimum scenario is for your fill to be balanced, meaning that each of these cavities are filling up at the same time, meaning that you have a runner set system set up that you have balanced flow. So if we jump back to SOLIDWORKS now, so this is my second scenario, and kind of the great thing about this is all I did was just did a move and copy command. You kind of saw when I initially showed the SOLIDWORKS that first part, I had it suppress the features. All I did was just a move copy bodies, and that's kind of the great thing about this is I just edited the initial part file, made a change in the geometry to include 6 of these parts, and then set up the runner system. So one thing I want to show right now is if I hit play, you can see how these runners aren't filling up simultaneously. These 2 over here are not balanced. What's happening is this runner system, we just assumed kind of a standard runner overall diameter, but this is not diameters that are conducive to a balanced flow. So the great thing about this, obviously some of you tool makers probably already understand. You're like, oh yeah, it's pretty easy to see. The 2 cavities closest to the runner have a very large diameter, and that's kind of if that you're probably already well aware of that. But one of the things that sometimes it's still iteration in terms of figuring out what the appropriate runner is for balanced running. So one of the things you can do actually with SOLIDWORKS Plastics is you can actually tell the program to solve for what the diameters are going to be for the runners. So with that being said, I'm going to jump. You see right here, I'm opening up another configuration for plastics. So this is my second configuration, which is going to balance the runners. And you also see the runner system was just drawn by a 3D sketch, and then just created the runner elements, which I'll show you in a moment. So as that loads, I'm just going to jump right back here. And I'm not going to maximize this, but so gate balancing. We're going to utilize SOLIDWORKS Plastics to determine the optimum runner size to maintain gate balancing. So you see in this image right here, everything has sort of the same gradient, meaning that they're filling up at the same time. When you actually look at the fill stage, it's going to show that each of these cavities are filling up at the same time. And you also note that the runner system is not the same. There's different diameters throughout the entirety of the model. So within plastics, they can actually calculate what those runner sizes are going to be to ensure continuity or balanced flow in your system. So let me come back to SOLIDWORKS. And you see right here, there's this option right here that says runner balancing. So in terms of how you set up a runner system is you ultimately, you go to your mesh, and ultimately you specify under your boundary conditions when you're ultimately working your way through the system where your runners are at by just clicking on the edges right here. And then upon doing that, you can specify what their default sizes is, but if you really want to actually go through the system and calculate the runner, what's going to ensure balanced running, what you can specify is, hey, I want to have a maximum diameter of this value, a minimum diameter of this value for my runners. I want to specify my maximum diameter at the inlet is this, and my minimum diameter is that, really however you want to customize it. And when you finish the scenario, if I hit show thickness distribution, this is going to show you how it's adjusting the runner design. So 0.215 inches here, 0.244 inches down here to 0.218, 0.102, 0.103, and this is going to ensure balance running. So you kind of see right here, the program is actually able to determine that runner size for you. Now, if we take a look at these results now, if I hit play, you see how it's now filling up, all the cavities are filling up simultaneously. And this is really important from a plastics design perspective because balance running is very important because you want to maintain, kind of have a consistent flow front across all your cavities. When I look at my results, that kind of ensures when I look at pressure values or temperature at end of fills, they're all kind of consistent across the cavities. So, great. So I come back to my PowerPoint here. So one of the things, kind of a quick webinar, but summary of plastics, you kind of saw that it's very easy to set up these scenarios. We start off with a single cavity with the windshield wiper holder, and then we jump to a multi-cavity mold. Very capable of handling balance running, actually setting up that runner system. Obviously, if you already know what your runner sizes are, you can also key those in as well. And it's very easy to determine pressure, weld lines, air traps, and warpage on parts. Obviously, this is kind of the tip of the iceberg of plastics. I didn't jump into inserts or overmolding applications, but there's a lot of other